In this lesson, we will do a little bit of review on sliding blocks. Here we have a block sliding along a horizontal surface. It then slides up an incline, goes up to a maximum height, and then slides back down. There is no friction anywhere. Draw a force diagram for the block at each of these locations. When it's sliding on a horizontal surface, when it's on its way up the incline, and on its way down. For this one, there's mg going down, and it is touching the surface. No friction, so only normal force. Normal means perpendicular, so this is the normal force. When it's on the incline, there is a mg going straight down. No friction, there's only normal force, which is perpendicular to the contact surface, and normal force is a pushing force. So you have normal force. And then on its way down, also mg going straight down. Contact surface gives us a normal force perpendicular to the contact surface and no friction. What if there is friction? Please draw a force diagram for the block at each of these locations. When it's sliding on the horizontal surface, when it's on its way up the incline, and when it's on its way down. You would have mg going down, normal force going up, and this time there is friction going against the sliding motion, so friction goes this way. And you have mg, normal force perpendicular to the contact surface. Since it's sliding up the incline, the friction would go down the incline. And then for this one, mg, normal force. Since it's sliding down, friction will be against the sliding motion up the incline. When there's no friction, these two forces would cancel. The net force is 0. That means the block would move at a constant velocity, no acceleration over here. For these two, whether the block is going up the incline or down the incline, we have the same force diagram. Since for both of these, the acceleration will be along the incline, so I'm just going to draw the force components along the incline. Normal force does not have any component along the incline, but mg does, and mg's component along the incline is mg sine theta. Same here, the component going down the incline is mg sine theta. Exactly the same thing. And that means the acceleration is, this is the net force equals to ma, so the m's cancel, the acceleration will be g sine theta going down the incline. And that is the same acceleration whether the block is sliding up the incline or down the incline. So for the block sliding up to the maximum height and then sliding back down, it goes through constant acceleration motion. Same acceleration the entire way, whether it's on its way up or down. When there is friction, friction goes this way with slowing the block down. So when the block is sliding to the left, the acceleration goes to the right, opposite to the direction of the velocity. So the block is going to slide slower and slower. When it's on the incline, the acceleration is going to be along the incline, so I'm just going to look at the forces along the incline. We have mg has a component mg sine theta going down the incline. The friction goes down the incline. Normal force doesn't have any component along the incline. And here we have mg sine theta going down the incline. The normal force doesn't have any component along the incline. Friction goes up the incline. When there is friction, the force diagrams are different. They're different, and therefore they have different accelerations. When the block slides up the incline, Both of these forces are in the same direction, so the net force has a larger magnitude compared to this one. Over here, they work against each other, so the net force is the bigger side minus the smaller side. The acceleration has a larger magnitude when the block is sliding up the incline than when it's sliding down the incline. Now see if you can draw a velocity as a function of time graph for the block sliding up and then back down the incline. Use up the incline as the positive direction. Do one graph for the no friction and one graph for with friction. Since this block does constant acceleration motion on its way up and down, and the acceleration is down the incline, negative direction, and the acceleration is the slope of a velocity versus time graph, that means our graph should have a constant slope, a constant negative slope for the constant acceleration. And of course, this is the turning point when the velocity is 0, which means this is when the block is at the maximum height. For this graph, the acceleration when the block slides upward is bigger than the acceleration when it comes down. So the slope is higher when it's going up, slope is less when it's coming back down. Not only the acceleration when it's going up is higher, it is also higher than this acceleration because over here the net force is only mg sine theta. Over here the net force is mg sine theta plus friction. So the graph should be steeper here than that one. And this net force is less than mg sine theta. So this one is not as steep as this part. And this is the turning point. That's when the block is at the highest point. As you can see, the area of the velocity versus time graph is the displacement, and this area is smaller than that area. That means when the block goes up, it does not go as high as that block when there is no friction. This makes sense because with friction, the block will lose energy to friction. So it loses mechanical energy to heat. Therefore, the block does not go as high as that one, assuming they start with the same initial velocity at the bottom of the incline. Just to clarify, when I wrote this, I was comparing the magnitude of the accelerations. Since both accelerations are down the incline, so they are negative in this coordinate system, meaning this acceleration, this slope, is more negative than that. And when there is friction, it would take less time for it to get to the maximum height, but it will take longer for it to come back down. And it takes more time for this eraser to slide back down. While this block, because it has a constant acceleration, it does constant acceleration motion the entire time, so the upward trip and the downward trip will be symmetric. If it takes 3 seconds for the block to get to the highest point, it will take 3 seconds for the block to slide back down. This part is just like something that is tossed straight up. It will reach a maximum height and then come back down. If we ignore air resistance, then the acceleration is g downward, whether the object is on its way up or down. So the entire trip is constant acceleration motion. That means the upward trip and downward trip, they are symmetric. If it takes 3 seconds to go up, it would take 3 seconds to come back down.